Hi, this is Mrs. Vrobel. This is part 3 of ionic compounds and metals. So the past 2 videos we talked about ionic compounds, how to name ionic compounds, their empirical formulas, properties, how to draw diagrams. Now we're going to talk about metals, and after we talk about metals we'll do a little nomenclature. So obviously you've learned through the periodic table and periodic law that metals take up a large portion of the periodic table, and that's true. And they have certain properties. One, they're shiny. So notice I have a piece of tin, and obviously it's very reflective, so it lets the light bounce off of it. It's typically metals are ductile and malleable. So I have copper wire here. So the fact that copper can actually be drawn into a wire, and it's very useful when we're conducting electricity, or we want to draw, I'm sorry, not draw, we want to make jewelry. A lot of your pots and pans are metal because they're very good at conducting heat and electricity. These elements from the previous unit that we talked about ionization energy. So the fact that you can remove electrons from metals readily is another property of metals. There are very few outer electrons in most metals, and that's the reason why they're very good at conducting heat and electricity. Okay. The way we try to describe metals, especially when we're looking at conduction of electricity, what chemists have decided is that the metal atoms, the reason why they're malleable is they have this sea of electrons, and this sea of electrons can be shared throughout a large area of atoms, and that's what keeps the metals from retaining their bond with each other. Also, the electrons, they aren't limited to just one atom. They can hop from atom to atom. So because of that, we call it delocalized. So they're not restricted to one atom. They're allowed to move around in a certain area. And because of that, we get a lot of formation of metal cations. Okay, so here is an example of a sea of electrons. So notice that these negative charges that are sort of interspersed within the positively charged metals, these electrons can flow from one atom to another. And because of that, we have what we call the metallic bond. And essentially, these electrons, we call that the sea of electrons. Because of that, it's very hard to break a metal. Now, you can break it. I'm not saying it's not possible, but it takes significant work or force to actually break a metallic bond. Now, this is from actually previous unit that we talked about periodic law. So notice that when you go across a row, the strength of the metallic bond actually increases. So as you go from left to right, the strength will increase. If you go down families, notice that's not necessarily the case. Okay, so the strength actually decreases as you go down a column. So if you want to increase metallic bond, you want to go to the right and you want to go up. Okay, the way you are able to draw a metal into a wire is the fact that you have this sea of electrons. So unlike the ionic compounds that we talked about previously, if you were to hit it with an external force, the fact that the metal cations hang together, and it's all because of this sea of electrons. So these electrons can move where they're most needed to balance the positive charge. Hence the reason why we have metals that are able to be bent into shape. Okay, so notice that ionic compounds, we said that most of the boiling points are high. That doesn't necessarily occur the same way with metals. Like, look at how tin, its melting point is actually pretty low compared to copper. Um, Here we have lithium. Its boiling point is 1,347, whereas copper, it's significantly higher. So you can't assume that all metals have high melting points, high boiling points. And especially when we're looking at alkali metals. So alkali metals are the first column in the periodic table on the left. They're very soft and malleable compared to things like platinum. So you can't necessarily lump them together because of that. Okay, alloys. So in lab, hopefully you will make this, which is essentially a brass penny. And alloys are solid solutions. So whenever you buy a piece of jewelry, you're probably buying a alloy. Even my wedding ring. Okay, my wedding ring, and I'll show you what it's made of in another slide. It's a solid solution. So that solid solution has the melting of two or more metals, and they essentially form a solution. So if you cut that metal, you're not going to see layers. You're going to see a uniform mixture of two or more metals. Okay, so here are some common alloys. So whenever you buy a piece of silver jewelry, you're looking at silver and copper. So silver by itself isn't as durable. So typically we add another metal to help make it stronger and also to reduce the amount of corrosion that you can have. Notice like the dime and the quarter, lots of times they reduce the amount of one metal because it's expensive. I mean, the actual penny is actually, the making of a penny is actually more money than the worth or the value of it. Notice how with steel, we can't just use iron by itself. Iron is not durable enough, and plus the carbon actually helps to reduce corrosion and strengthen the material. Stainless steel, you see that a lot. My computer is made of stainless steel, and they throw in a little bit of chromium with that carbon and maybe a little nickel to give it that nice sheen and the reduction in corrosion. Lastly, brass. So when you make your brass penny, you're essentially combining copper with zinc. And one, it gives us a really pretty appearance to whatever object we're trying to make it with, and also it reduces the amount of corrosion. Okay, my wedding ring is actually white gold. So when the jeweler made my ring, they combined silver, gold, or palladium. Okay, it's it's one of the popular pieces of jewelry now, and gold by itself, if you were to like bite into it, the prospectors, they used to chew on it a little bit just to see if it was soft enough. Gold by itself is too soft, and especially for jewelry that you wear every day, you don't want pure gold. So obviously you need to have an alloy, and that alloy typically strengthens the metal. Now, the challenge with alloys sometimes is if you're wearing something for periods of time, you're actually removing layers of the metal. And notice my my wedding ring, because it's coated with another metal, it probably needs to be replated in the near future. Okay, we're going to do nomenclature, and I just want to highlight a couple of these before we move on. When you're looking at nomenclature of metals, okay, you need to look at if it's a transition metal. So if it is in the middle of the periodic table, it's going to have a Roman numeral associated with it because there could be more than one charge. If it's in the first two columns, you don't have to worry about it. But if it's in the transition metals section, you do have to worry about it. Notice that you name it first. So metals are always named first, non-metals are last, okay? And non-metals get the IDE ending. Don't forget, and in your homework, you're going to have a polyatomic ion, okay? So you have to look on that chart for the polyatomic ion in order to name it. Okay, here we go. So here's our transition metal nomenclature, and like I said, they have Roman numerals. Now, the good news is with Roman numerals, that pretty much tells you the charge on iron. So I'm just going to write this down, Fe. Remember, it's Fe, not Ir. The Roman numeral designates the charge on the transition metal. Now, you also have to look at what is the charge on chlorine. So I'll go back to my handy dandy